we've seen that consistency parsing and dependency parsing. For now, let's say we'll look, let's say, at dependency parsing, but we could use either of them. And what we will do with this knowledge is that instead of trying to solve the problem of visual question answering by just embedding the question directly, we'll go step by step. And so let me show it here. Is the bus full of passenger? Whoops. Yeah, full of passenger. And so the subject here, you could say the verb is the root, the subject is the bus, the determinant, and then you have is full, so together, and then we have the passengers. And so we have a nice, here in this case, a dependency parsing of this. And when you have this, it kind of gives you some nice way to address this question. And the idea here is what are the main two pieces, like the leaves? We talk about passenger and we talk about buses. So why don't I start and look at buses, and I look at passengers or people, and can I find these? And then maybe I can combine the two together, and then I can see if they match the concept of full. And so that's what's called in the world of neural module network a computation layout. And what's nice now is that instead of very fully data driven, where you hope that your RNN or transformer will contextualize things correctly, here we're going with the knowledge from syntax and language structure by saying, what are the noun phrases? Find my noun phrases in my sentence. Let's find them in the image. Let's just attend to them and find an embedding. And then if, for example, I want to bring these concepts together, and then I want to know if like, in fact, the measure will be the full. Is these bus and full, are they combining together? Are they the two together? So this is an example of a computation layout. I talk about using also, this is a computational layout we're using dependency parsing. I also hinted about using consistency parsing. In that case, it will be looking at noun phrases, and it will be looking at verb phrases. In the case of the original neural module, in this case, they use a different approach, and there they look more for the dependency parsing. So you, in this case, look at the concept of full, the concept of bus, and here the bus is easy, the full will be hard. And then you bring the two together, and is one is bus is full. You can, what's nice with the module network, it's less like the specific of these modules, but now I can, I'm gonna learn end to end to fine tune each of these modules and also the full task together. The full task is to answer like visual question answering, but the subtask is to have to also train each of these modules to perform as well as possible. And in the original module network, they predefined these, and that's why I kind of like the concept here is that that the neural module network is that I can take external knowledge and put it in it. And how do they do this? Is like they look at the parsing, and then they define those modules themselves. It is a little bit arbitrary. That's their decision. It could have been done differently, but they decided to define a subset of module. And I don't want you to get overhang on like these exact module. I think these are fair, these are good module, but there's a lot of other module you could have probably done, but these are a good starting point. They decided, hey, I will have one module to attend on object, give me any concept, and I'm gonna tell you where in the image it is. And then I will just have a module about combining different concepts. So if I don't know, I have a green and a house. And so I could have everything that's green and everything that's a house. And then I bring the two combined together. And so I have a greenhouse together. So that's the concept of combining. But then I also have a task in mind, and so what is interesting is that I have a task in mind, and the task I'm going to condition on language, and that's interesting here, is that instead of having a task of like, is it that location, or is that object present, or is the glass full, or like you could think of all of these. Instead of that, they're like, hey, give me a verb, or give me something, like give me a word, and I'm going to use this word with the image and to up to now what you identified to finally decide on the final solution, like the final answer. And so they define kind of a classifier condition on a word. And that's I thought was quite interesting. And finally, they said there may be different ways of doing prediction. In some cases, it may be that that I want to condition, or maybe I just want to go directly on all of the object and just find it, is it there or not? Like maybe some questions are so obvious that I can just go and just look at the attention map and to find, is it there or not? So this is the interesting aspect. So the take home, and I'm going to talk about extension on how to optimize and everything automatically, and the computation graph. But the intuition here is that you have a problem that's relatively complex, and instead of like putting everything maybe on one giant, let's say, transformer and just hope that everything works, I'm saying, hey, can I split it in pieces? And instead of having all of these pieces the exact same unit, like we have in a tree LSTM, here we'll have dedicated modules. And these modules will have different aspects to it. So they will have one module, and then I can use my knowledge to define what those modules could be. And then I will need a kind of a deterministic way of taking any kind of input, like a question or a statement, and create a computational graph. So I have, as input, I have a sentence, and I have a possible set of modules that's kind of predefined. And then I'm going to create, for that specific input, I'm going to create a computation graph. And right now, this is the kind of deterministic based on the parsing tree. I'm going to tell you about it in a second on how to make it so that the computational graph is also learn how to create a computational graph live as well. So so one of the interesting thing here is that when this, right before this neural module network came out, there was this really cool data set that had been suggested, which is called the Clever. And for many of us, we were like, oh, it brings some very complex question. And so for these very complex questions, we want to be sure how we're going to solve those very complex questions. And it sounded like it will take us a year or two to solve that. Or not a year or two, but many years to do. But it turned out the neural module network was just perfectly designed for this kind of data set. Because although the questions are very complex, they had been created by a computer, or some of them at least were created by a computer. So if you create those questions, they look complex for a human, but if you can slice them well, they can be really nicely created. But I said one of the challenge with the original neural module was that how do you go from my input to a computational graph? And one thing that I liked about this was to let's use an RNN, and why did they use an RNN? This was at that point the kind of sequence modeling you could use. Probably need these days a transformer or something else to do this. But what was interesting is that they used an RNN to decide what to do next. So you have a bunch of module, and let's say for now they're predefined module, but to decide which module to do, instead of making it as a graph and run through the graph, what I will do is make it as a sequence. And I make it as a sequence of modules. And then each of this will also be connected together, but it has a flavor in a little bit in a stack network kind of stack LSTM. But yeah, the RNN is going to be able to predict which module to use. And then I have a sequence of it. And then once I get that sequence of it, then I can get finally my answer. So this is a nice way of taking it in an end-to-end manner. So for many of your projects, as you look at this, try to think of like maybe some of those more interpretable approach, interpretable, and also one where you could put more knowledge, because this is a really small set of modules, but for each of your problem, you could probably imagine having other kind of module. And so that would be something to think about. One thing I want to show is an extension of neural module network, which goes beyond that to try to make it even more interpretable. And like any good paper come with a good title, neural symbolic network. Neural symbolic network is an extension of the neural module network, but it comes both at a price, and but it also comes with great advantages. The price is that we're going to take some very complex representation of both vision and acoustic, and we will make it discrete. Or very interpretable or very simple. We're going to simplify, like instead of having 7,000 dimensions, I'm going to force it to be simpler. And we could call it like kind of attributes of an image or a language. So I simplify, but by simplifying my representation, both visual and maybe also you could do the same for language, but specifically for visual, it comes at a great advantage that I will improve my interpretability. So in typical approach, I will get my mask RCNN, but in a typical approach is for each of these RCNN, I will have like maybe a vector of 3,000 for each of them. Here, what they do is I will train on another data set. I'm going to pre-train on another data set. In fact, I may not even fine-tune it. I think in the original paper it was maybe not even fine-tuned. I'm going to train on another set to be able to predict different attributes of the objects, like small versus large, or cube versus cylinder, or the type of metal, or maybe the position. Well, the position I can get directly from RCNN. And so I go from a vector of maybe 3,000 to some very concrete attributes. So this is human interpretable attributes. And so that's a good advantage. So that will be my here. And then for the question, then what I will do is a lot more like the neural module network, is I will take my question, and I will, in this case, they had the the extension of the original neural module network, where the computation graph is defined based on the encoder. And then from this, I get a sequence of kind of a program. Instead of, it's a computation graph, but it's a sequence computation graph. So you could call it a program. And then instead of running the program on the CNN, I'm going to run it on this. So this program will be, instead of taking as input maybe the object, the RCNN output, they will take these. And so the first step is similar. And so you execute these. And if you really wanted, like, very simple, you could make these whatever you want. I mean, if you want them to be very interpretable, you could make them rule-based systems here. So filter shape, maybe a rule-based or decision tree. You could make them as, so now if you make this very interpretable and my input is interpretable, my question was parsed in something that is interpretable, I get something quite interpretable at the end, because then I can take any of these programs and apply it on my interpretable input, get a new interpretable output, and then I can get finally my answers. And hopefully I can solve through that some things like counting, which has been a challenge for many, for a long time in these, for a long time, meaning a year or two. Yes. And so this is just an example output from the original paper, where the neural symbolic VQA, where the nice thing here is that the neural symbolic programs more accurate answers, but also it's interesting to see the kind of program that has been run to this. And so by being symbolic, as long as I got an attribute that is related to the question, and this kind of world is like all of the question in that world were kind of identifiable, and there was a nice way of creating attribute. The challenge is, how do you scale this to a world that where maybe the dictionaries is not as easy to do? But that I leave it to you guys to in your project maybe to explore that. An extension for neural symbolic was to learn visual concept, word, and semantic of sentence without explicit supervision of any of them, just by looking at images and reading per question. So that was a nice extension. So this is a little bit more in the world of self-supervised. I just give you a question and answers, and I give you this, but I don't give you what those specialized modules should be. And I want you to learn them. I don't tell you yet what the concept should be. And then I want you to learn that automatically. And that was a nice aspect of that line of research into this. Another extension that is just explaining one way to do this, and some aspect of it was with reinforcement learning. So I'm pointing to that. We'll discuss more reinforcement learning in 2 weeks. But I think it's a really, the basic aspect of it is that I certainly, the concept in itself, there's a small chance that those representations are not as human interpretable. That's still possible, but hopefully they are. And so a concept, you will hope that those concepts are human interpretable, but there's, I mean, unless you do the previous approach, it's still an open problem to improve this. And I want to share, this is just another example where the concept, but the problem is, how do you name those concepts afterward? And then what's nicely is, like, you go and look at this, and then you can find which objects are selected, and then you can give it, and that goes the same when we were doing topic modeling for language as well. Okay, the last part, I just wanted a few slides on this. It's more like for entertainment at the end for the last 2 minutes. I thought it was interesting because we talk about translation, but sometimes it's good to go a little bit beyond what everybody else is doing. There's one paper I wanted to bring, which was really interesting, which was take an object and hit it. And for now, let's say I hit it always with the same wood. So it will be quite different from, I'm not going to hit my cell phone too much, but the sound is different. And so the idea was, like, can I detect object just by how they sound? That was really interesting to me. And so that was one. Sound of pixel was a really interesting extension. Sorry for the whole graph, but what I wanted to show here is that you get a lot of video, and there's a lot of video with audio, and what I would like to do is, I don't tell you where the sound comes from, but because you see so many videos of people talking, you will realize that there is a correlation with lips moving and some sound, or maybe with violin or some instrument. So I don't tell you that a voice always comes from the mouth, that the guitar comes from a specific visual, but you can do all of this automatically, and so you learn just from video on YouTube, unannotated videos. It's paired data, so you have audio and video paired, and then you can learn what's called the sound of pixel. And what's really interesting is, I just put one of them, but there's about 5 papers in less than 6 months that all did the same thing in slightly different way. That's also sound. And the last one was speech to face, and that comes with a lot of downside, and that's why we have this lecture in a few more weeks at the end of this about bias and issues with this. But yeah, speech to face, the idea is, given a voice, can I estimate the age, gender, or maybe ethnicity of someone? And so you get the voice encoder, you encode maybe the face, and then decode the face. That's for training, and at test time, you can just from the voice decode the face. So these are some applications. I also wanted to make you think about your research. This is not the only topic, but thinking about fairness and this, when you look at your research, is something important. And so I want you to also think about these issues. Thank you very much for your attention.